Welcome to Titration Video number 2. Alright, so we left off right on this slide right here. So let's take a look, see what we got going on here. Alright, so if you remember, we easily calculated the moles of HCl. Now notice we're not calculating the moles of NaOH yet, because we already know what the moles are based on it's a 1 to 1. So what we're going to do is we're going to use the moles of NaOH to take the volume, and moles per liter give you this concentration of NaOH. All right. Let's do another example like that. The NaOH solution from the previous example was used to titrate a 28.6 milliliter hydrogen bromide solution. The endpoint was reached after delivering 34.85 mils of titrant. Find the HBr in the original solution. So what you have is this HBr where you don't know the concentration. Yeah, it's strong, and yeah, we're titrating it with a strong base. All right? And that solution from the previous example is being used to do the titration here. So you remember we have the volume, and then so we now have the concentration. So you can use that in this to figure out how many moles of NaOH, and then figure out the concentration of this. So this 0.238 moles per liter, if you will remember, was our answer for this guy. So that's why we worked so hard to get that concentration, so that we could figure out the actual moles of NaOH in that volume. Okay? So now we use the same logic that we did before, and we say if we know the moles of NaOH that were used to titrate this, then we know the moles of HBr. All right? And we know that the endpoint was reached because it changed color, so that at that point the two moles amounts are equal, and notice that we have a different volume this time, so you take that equal mole amount divided by the new different volume, and that's your concentration of your HBr. So kind of just piggybacked on the previous problem with that one. Okay, so as we talked about, it probably gets a little bit trickier with a weak acid, strong base titration. This is a common acid that is used. The name is escaping me now. Sorry about that. But it's I haven't done that since college. I don't think we've used that one, but it's fairly common, and it's nice to use because you can weigh out a gram amount of it, and then since it's a gram amount, it makes a very accurate. We'd be able to go one place even farther than that to standardize NaOH. Now NaOH is kind of all over the place. You can try to get its molarity pinned down exactly, but there's a lot of variation in it, and it's just sort of the nature of the beast. So it's really hard to do a standardization and say, I'm going to make an exact concentration of NaOH. You can find out what that concentration is by taking a standardized weak base that is solid, and KHC8H4OH is one that's used for that. I promise you I will get you the name of that eventually. Okay? So anyway, the endpoint was reached after 42.55 milliliters of the NaOH solution was delivered. Okay, and so we're going to look at this. We have these known amounts here of potassium, hydrogen, potassium hydrogen phthalate. I believe that's it. Starts with PHTH. Phthalate. Can't believe I forgot that. So this is potassium hydrogen phthalate. And then you can take that aqueous solution and react it with the strong base. Now the strong base is going to rip off the hydrogen, which is it now becomes potassium phthalate, because the hydrogen right there, the one that's kind of separated from the other one, that's the one that gets ripped off by the strong base. Okay, so the moles of potassium hydrogen phthalate is pretty easy to calculate. You simply take the grams and then look up the atomic weights using your purple sheet. Circle square method if you want, and boom, that's one of the reasons it's so nice to use. You can figure out the concentration pretty easily. You just get the moles, and you got that to 4 sig figs, which is pretty darn nice. Okay, now to figure out the concentration then of the NaOH, you know that every one of these OHs got herself a hydrogen. Okay, that's just the way it went, because she's strong. And so I'm going to pull that hydrogen off, make that water molecule. So you get this 1.54 times 10 to the minus second, because it's the same as the concentration of the NaOH, because like I said, they will take every bit of it, so they'll be equal. So with strong acid and strong base, they were totally equal, but this one, you know, you can count on the strong base taking every last one of those hydrogens out of there. Therefore, that's going to be your concentration there. Okay, so the volume right there, turn it into liters, that gives you your concentration, your molarity of NaOH. So this will then serve as a great standardized solution. There's no way that you can make a solution of sodium hydroxide that you know the molarity that well. That's what getting a standardized solution means. You use a solid form of the acid. That's really easy to weigh out and do that. All right. So the NaOH from the previous example, we'll piggyback on the problem just like we did on that other one, is used to titrate this much of a weak acid, 25.65, your acetic acid. The endpoint was reached at 28.40 milliliters. Now find the concentration of that unknown acid. So first thing we're going to do is we're going to find the moles of NaOH delivered. Now remember, we just used a standardized acid solution to get the exact molarity of that NaOH. And it's that many moles per liter. And then if you take an exact volume amount, you can get 4 significant figures in your moles of NaOH. And of course, you know that's strong, so it's going to take every last one of those hydrogens. So you can say that those two things are equal. So notice you can do this with strong acid, strong base, and weak acid, strong base. It works the same way. Okay? So here, there's your volume, divide it out, and that's your concentration of your unknown acetic acid. This might be the type of lab that we do for next week. For those of you that are going to be doing your lab next week. A weak acid, strong base. Another third example right here is you have a sample of acetic acid being titrated with NaOH. And then it asks you three questions here. First one is determine the volume of 0.50 NaOH that must be delivered to reach the half equivalence point. Okay? So let's talk about what that is. What is the half equivalence point? Well, remember, first thing we want to do is we want to take that 30 liters of solution with the known concentration and then turn that into moles. All right? The volume of NaOH that must be added, we're going to start with 0.0075 moles of NaOH. And see if you can figure out where that number came from. Hit the pause. Welcome back. If you said it's half equivalence, so that's when you're halfway there, and half of 0.015 is 0.0075, then you are right. That is correct. So that is how much NaOH must be added to get to the half equivalence point. It's just a term that says that you're halfway to the moles that you need. And as it turns out, when you divide that, and this, of course, you're starting with the moles, and then you do the concentration kind of in reverse. There we have 0.015 liters of solution. So that's the whole solution. And that's just a kind of a little coincidence that those numbers are the same, because this is moles of acid, and this is liters of the entire solution. Okay? Now, at that half equivalence point, the pH was measured to be 4.74. Find the pKa, weak acid. When you think of pKa, think of weak acids. Certainly that is something. Now, remember, here's one of the definitions. The weak acid and its conjugate base are going to be equal at the half equivalence point. Okay? Because it's half gone, and the new stuff is half formed. Okay? So that's halfway there. So, therefore, you can use something that looks an awful lot like the Henderson-Hasselbalch equation, and you got the pKa plus the log over those two concentrations. Well, here's the thing. If those two things are equal, they'll cancel out. Okay? So what we're saying is the pH equals the pKa at the half equivalence points for all weak acids and bases. Okay? And it's because of this. If you were asked to demonstrate why that is, you know the Henderson-Hasselbalch, if those things are equal, the log of 1 is 0, and you've got 4.74 equals something plus 0, 4.74. Okay? So that's B. And then C says, identify the main species that are present in the solution being titrated at the half equivalence point. Okay? And I don't think that they had the